Hello everyone. In this presentation, I am going to discuss about the role of dark matter halo angular momentum distribution on bar formation and evolution in these galaxies, typically like Milky Way type galaxies. So as we know that our Milky Way galaxy is surrounded by a dark matter halo, for which we know there is a distribution of particles in the dark matter halo, which has negative angular momentum as well as positive angular momentum corresponding to retrograde and prograde orbits. So this is a typical distribution where these retrograde and prograde fractions are equal at all radii, and this corresponds to the overall angular momentum of the halo to be 0, and which makes the spin of the halo to be 0. And how we define spin? Spin is defined in terms of a total angular momentum divided by the mass within a given sphere, which we typically take virial radii, and v is the velocity at the virial radius, and r is the virial radius itself. So we have this spin value, which is defined by Bullock in 2001, who accounts for who measures this spin value in cosmological simulations using this formula, and found that the spin distribution peaks at around 0.035. And now coming back to this our work, where we are seeing that there is a huge range of halos. Typically there are a lot of halos varying from spin 0 to 1, and for a given spin there are numerous distribution of prograde and retrograde fractions are possible. So that's what we target in our work, which is Kataria and Shane 2022, where we look into the prograde in this region, which is we basically focuses on the region less than 30 kiloparsec, and we gradually increase the prograde fraction. Basically we are making some of the retrograde particle to the prograde by reversing their tangential velocities, and we find that spin increases, and we make the n-body models and evolve with the gadget core, and we find that the models with the higher spin forms bar earlier as predicted by earlier studies, but we also find that in secular evolution the bars keep on growing, which was not the case in the previous studies like Saha et al. 2014 and Long et al. 2014, where they find that there is a secular dampening in the growth of bar. But in our case, we see that bar grows, and the BPX purge is much more pronounced if you have a high spin or high prograde fraction in the central region. So this was one of the key results. And second result, we find like all the bars are slow irrespective of the prograde fraction within this certain region. So basically, tremendously, we want you to dive deep to know why some of the halo are showing secular growth in secular evolution, while in our case it is not showing that. So that mystery we answer in our next project. There is still exciting results from that paper I'm coming to. Before going into that, we explored the whole range of prograde and retrograde fraction using a detailed study, which is this Shiba and Kataria 2024. In this, we have a parameter called lambda, which is basically controls how much prograde or retrograde fraction we have in a halo. So in this, we don't restrict ourselves to the 30 kiloparsec region, but all the radii. So basically, if we have lambda is equal to -1, that corresponding to we have all retrograde particles. Basically, we are reversing all prograde particle to retrograde. So we don't have any particle with angular momentum greater than 0. And if lambda is 1, then all particles are prograde. Basically, we are reversing all the retrograde particles to the prograde particles. So and the fraction in between will control basically we'll have the mixed number of prograde and retrograde particles, and it will increase as we go from -1 to 1. We will have more prograde particles. Now, so once we have controlled our halo, then we perform the analysis of torque experienced by bar using three approaches. One approach is the analytical approach, where we use Lindemann and Carolin's torque formula, and we see that different resonances, if you have put the bar as a perturber with a given pattern speed, then different resonances react differently. And the major resonances like co-rotation and radial resonances, they behave oppositely, and there are many other sub-resonances which also plays an important role. And but what is the key result, key resonances which is playing in this torque formula is the radial resonance, and we see that as the prograde fraction increases, you see that torque experienced by the bar in this halo is decreasing. Not this axis is a negative, so basically the negative number is decreasing. Basically you can see that torque experience is also reducing. Now, and then now we once we have performed this analytical analysis, we perform the test particle simulations with the same models, having the similar setup for the various prograde fractions, and we find that again, with increasing the prograde fraction, our model shows, like initial behavior of this model shows that the bar experiences lesser torque as you increase this you increase the prograde fraction. And once we have confirmed with these two methods, we also want to test another method, which is the n-body simulations. We make model with the increasing prograde fractions, going from -0.4 to +0.4 of lambda values, and we see that torque value reduces. And that's why our results are pretty robust, because we are saying with the three methods. And we are updating Weinberg 1985 results, which was just opposite of this. And the reason that was a semi-analytical paper where they looked into various resonances. I think they neglected some of the resonances, and which made their results to be opposite. And now we have also confirmed with Weinberg about our result. He also agrees with our finding, and that's kind of quite robustness in our result. Like, we are having three methods, and also agreement from the previous author who worked on this. And then another interesting thing is, this results can explain the low surface brightness galaxies, which are typically thought to have a high spin, and because of their high spin, basically they come into this region, they will experience lesser torque, and because of this lesser torque, bar will not be able to grow, and we find that most of the LSPs have weak bars. Now coming to the discrepancy which we are talking about, why in the previous studies people are finding that bar is not growing in the secular evolution. Basically, BP expulsions are not so strong, but in our previous case, our this recent study showed that we can still grow bar in secular evolution, and can have a highly pronounced BP expulsions. And it has a huge consequences on the Milky Way type galaxies, because our Milky Way has known to have BP expulge, and we would like to know which halos, which kind of spinning halos can promote these kind of bulges more. And given these discrepancies, we wanted to dive deeper. So we ran a lot of model with a lot of permutation and combination with this retrograde and prograde fraction. Then we come up with one explanation which resolves this contradictory results from our work and previous work. So we can explain this with these two models. We have generated a spin 1.01 for both the cases. And one halo has a continuous distribution of halo angular momentum, and basically there is no discontinuity at Lz is equal to 0 as we switch the particle from prograde to retrograde. While in another case which is having discontinuous halo angular momentum, and we see that there is a huge discontinuity at Lz is equal to 0 in angular momentum distribution. But the overall spin in both the models are same. Basically they have a equal number of total angular momentum. Now once we have made this model, we evolve this n-body models, and we find that bar in the discontinuous case doesn't grow and it's much weaker, and the bar which is in the continuous case, it grows heavily, and it also have a pronounced PP shaped bulges. So you can see that the same spin model with the different discontinuities. So that's how we can explain our results which didn't have much stronger discontinuities, but the earlier works by Long and Saha, they had this discontinuity. So because of this, we find such a variation in the bar strengths. And this is nicely explained in our recent paper, Kadaria in 2014. If you have any further question, you can please write to me. Thank you.